Now, we will continue the discussion from where we left. We were discussing how to solve the second order differential equations, right? Homogeneous second order differential equations. We use a change in variable, right? And then we transformed into the system of first order differential equations. Then we use the matrix methods to find the solutions, correct? Okay, let me go back and review what we discussed so that quickly, you know, okay, that's what we have, right? We made the change in variables. We got the system of first order differential equations. Then step 0 is to find the critical point. Step 1 is to find the eigenvalues. Step 2 is to find the eigenvectors. Then you write the general solution. You sketch the phase portrait, and then you classify the critical point. That's been our story for the last 1.5 lectures, right? And we also know that each eigenvector is a solution and the eigenvectors are linearly independent, and that was established by the fact that the determinant turned out to be not 0 or Wronskian is non-zero. Do you agree with me on that? Yes? And then what we did was, we had, I think, some 9 different or 10 different cases coming up from this. We covered about 5 cases where you have case 1 is when eigenvalues are real and different. The next bigger case is when the eigenvalues are complex. The third bigger case is when eigenvalues are complex. Okay? So we worked only on real and different eigenvalues. When you have real and different eigenvalues, you could have real and different, but they are negative, real and different, they're positive, real and different, they're of opposite signs, and one of them is 0, the other one being non-zero, right? Those are the 5 different cases. So we said, okay, the general solution would look like that, and we saw the pictures. When the eigenvalues are real, and different positive, the solution, when we run through the procedures and when we sketch the phase portrait, we can see that the solution curves are going away from the origin. So the critical point is the source and the critical point is unstable. Clear? And when your eigenvalues are real and different and negative, all the solution curves are going to the origin. So this origin is the sink or the attractor, and the critical point is asymptotically stable, right? And if your eigenvalues are real, different, and of opposite signs, then the solutions are never going to 0. So the critical point is unstable, and the critical point is a saddle point. Okay? And the last case that we saw was if your eigenvalues, one of them is 0, then instead of getting one, your matrix A would be, the determinant of the matrix A would be 0. So it's a singular matrix. So you do not get one critical point. Instead, you get a line of critical points. If the other eigenvalue is negative, all your solutions go towards the line, equilibrium line. If the other eigenvalue is positive, all the solution lines go away from the equilibrium line. That's what we have seen. Is that clear? And we don't classify that if one of the eigenvalue is 0, we do not classify the critical point. We do not discuss the stability of that critical point. Make sense? All good? Yes.
What if they're equal to each other? What if eigenvalues? What if lambda 1 and lambda 2 are equal?
They will be equal. Okay, so that's the next case. Like I said, the next big case would be, today I'm going to focus all our time on complex eigenvalues. Maybe on Thursday I'm going to get to the place where the eigenvalues are equal. So we are going to take that story. Yes? So yes, forward, and then that's what is going to happen on Thursday. So last week eigenvalues were real and different. Today the eigenvalues will be complex, and on Thursday, starting from Thursday, eigenvalues will be real and equal. Clear? Are you all good? Any questions? No question? Okay. So let's go to this today's portion of the lecture. It's going to get interesting. Hopefully you will like it. Okay. And yeah, let's begin. So your A is a 2 by, I mean my discussion is going to be just based on 2 by 2 like how it happened in the previous 2 lectures. But this theory can be extended to the matrices of 3 by 3 and 4 by 4 or any square matrix. Okay, not for the rectangular matrices but square matrices, because you can only find eigenvalues for the square matrices. So this discussion can be extended to any of the square matrix. Now specifically I will be dealing with 3 by 3 or the higher order matrices, like once I finish the 2 by 2 case. Okay. So now today we are going to discuss the complex eigenvalues. So my matrix A is a 2 by 2 and my eigenvalues are complex. Okay, the complex eigenvalues always appears in pairs, right? The complex conjugate. Don't sit in the first row and look at the cell phone because I get distracted. At least keep your cell phone down so that, or hide them or something like that. So if your eigenvalues are complex, they always appear in conjugates, right? They appear in pairs. You can have either 2 complex eigenvalues, 4 complex eigenvalues, 6 complex eigenvalues, but you can never have 3 complex eigenvalues. Does it make sense? First thing is that. The second thing is, okay, now let's say your step 1 is to make sure that what is your critical point. You're going to do that. Then step 2 is to find eigenvalues. Okay. Step 3 is to find eigenvectors. So the eigenvectors are going to be this. These are 2 eigenvectors. By the power invested in me, you're going to trust me for now that those are the formulas. Yes, you're going to memorize it and you're going to write down the eigenvectors, and your general solution then is going to be x equals c1 x1 plus c2 x2. Okay. And of course each eigenvector is a solution of the system. They are linearly independent because the Wronskian is non-zero, so they form a fundamental set. The whole thing would remain the same. What is different is that in the previous, when my eigenvalues were real and different, my eigenvectors were e to the lambda, when the eigenvectors are real and different, my eigenvectors were lambda 1 t times v, x2 is going to be e to the lambda 2 t times w. This is what I had. When my eigenvectors were real, when my eigenvalues are real and different, but when my eigenvalues are complex, these are my eigenvectors. So the difference comes in only in eigenvectors. Rest of it would remain the same. The process remains the same. Everything remains the same. Is that clear? Are you with me? Clear? Don't write anything because this is already online. As you know, I already uploaded blank lecture note. I will upload the completed lecture notes as well. Nothing is different. This has been done for the very first time, I think somewhere in late 1800s or early 1900s. So it's been 100 years. Things have remained the same. Okay. Then how would my phase portrait look like? I mean, some examples of these. If your real part is negative, then what happens is all my solution trajectories go to the 0. In such a critical point is sink, but when they are going to 0, they are going in a spiral form. So that's why it's called a spiral node or a spiral sink. When your real part of the eigenvalue is positive, all the trajectories go away from the origin. They become unbounded, they become infinite. So such a critical point is called a spiral node. Because they are going away from the origin, it's called a source. So it's called a spiral source. Okay, it's a repeller. Now, if if the real part is 0, that means your eigenvalue is purely imaginary. That means it's not going to 0. It's not going away from the 0. It's circling around the critical point at a certain distance. The distance doesn't change. It's like a cruise control. Once you set it at 60, it remains in 60. Do you understand it? So something like that, and it's going in a closed loop around the critical point. So the critical point is called a center. Because it's not going to 0, it's not asymptotically stable. Because it is not going away from 0, it's not unstable. Instead, it is just stable. Is that clear? Stable means it's going in a closed loop at a certain distance. Asymptotically stable means it goes to 0. Unstable means it goes away from 0. Okay? Good? Okay. So now that's the theory. So let's begin our discussion. It's going to be a long drawn out battle. Keep yourself together, don't give up. And hopefully at the end of the class you will find it nice and rejuvenated. Okay, so this one is pretty straightforward. Meaning, what do I mean? Is it okay to say my step 0 is, here you can say my matrix A is 0 1 negative 1 0, and determinant of A is 1. So A is non-singular. Because the matrix A is non-singular, A inverse exists. So that gives you x equals 0 is the critical point. Remember, 0 means the origin that I'm referring to. So 0 0 is the critical point. Are you okay with that argument? We have seen this before, so I just did not give you the entire details. Are you okay with that? Is there anyone who wants to see the details one more time? So the first thing is 0 0 is a critical point. Good? Okay, the next thing is I want to find eigenvalues. So what are my eigenvalues? I need to find out. Okay, so lambda squared minus lambda times trace plus the determinant is equal to 0. So in this case I get lambda squared minus lambda times 0 plus positive 1 equals 0. So you get lambda squared plus 1 equals 0, and you get lambda is going to be plus minus I. So in other words, from here I can say that the real part is 0, the complex part beta is the coefficient of I, so that's going to be 1. Is that okay with you?
What's the trace again?
Say it again.
What does trace mean again?
Trace means sum of the elements on the main diagonal. So trace is that. Sum of the elements on the main diagonal. You all okay with that? All good? No surprises, right? Nothing has changed. Except that previous case I used to get my eigenvalues as 2, 3 or negative 2, negative 3 or 2 and negative 3, basically real numbers. But now I got a complex eigenvalue. I want to tell you, this is very important. Alpha is the real part, which is 0 in this case. Beta is the imaginary part. It is the 1 in this case. Remember this, because after the whole discussion you should not think where did I get alpha and beta from. Okay. Now that being said, okay, that being said, now then what is my next goal? My next goal would be to find the eigenvectors, right? So so I want to find the eigenvectors, so I'm going to put lambda equals I. So when I substitute, lambda 1 equals I, so this is going to be A minus lambda 1 times I V equals 0. So when I do that, 1 equals I. So when I do that, you get negative I 1, negative 1, negative I times, V1, V2 equals 0, 0. So this gives you negative I V1 plus V2 equals 0. So that gives you V2 equals I V1. So your V is going to be V1, V2. So this is going to be V1 is going to be just a V1, and V2 is going to be IV1, and my eigenvector is going to be 1I when V1 equals 1. Do you agree with me on that? Some scalar multiple of that. Clear? Are you all good? Can you all hear me clearly? Why is it like that? I don't know why this is like this. So let me erase this so that write it in a different So my eigenvector is v1, v2, so that I write this as v1 in iv1. So that gives me 1 and I when v1 is 1. Do you agree with me on that? Yes? So now I want to write my eigenvector as 1, 0 plus I times 0, 1. So my real part is B is the real part of V, which is going to be 1, 0. And B2 is the imaginary part of V, so that is going to be 0, 1. I'm demonstrating the process for now, so please be with me during this process. At the end of the problem, if there are any loose ends, we will tie it up all together. Yeah.
Is it RBV?
Real part.
Okay.
A real part of the V and Im is the imaginary part of the V. Okay? Are we all together? So one more time, alpha is the real part, which is 0. Beta is the imaginary part, which is 1 for the complex eigenvalue. Here, B1 is the real part of the eigenvector. B2 is the imaginary part of the eigenvector. Is that clear? Now, just a hypothetical question. So if my lambda 2 is negative I, what do you think is going to be my eigenvector? Can you, any guesses? 1 negative I. It's going to be the complex conjugate of that, right? So does it make, are you with me on that? But I don't need this because they are complex conjugates. I don't need this. I can just work with this one. Why? Just believe me for now. I'm going to come back and tie the loose end after a certain point of time. First, I'm explaining, okay, what is the process? How do you get the solution? All that. After that, I'm going to give you the backstory. Okay, I can choose to give you the backstory first or at the end. This time, I'm choosing to give it at the end. That's all. Clear? Are you all good? Okay, so now what is my general solution? My general solution is x equals c1 x1 plus c2 x2. What is my x1? x1 is going to be e to the alpha t, b1 cosine beta t minus b2 sine beta t. X2 is going to be e to the alpha t times b1 sine beta t plus b2 cosine beta t. Now where are sines and why are sines and cosines appearing? Where are they coming from? All that I will address that at the backstory. Right now, I'm not giving you the formulae on the test. You're going to memorize them and you're going to write them. So your x1 is going to be, remember your alpha is 0. Your beta is 1, your b1 was the real part, which is 1, 0. Your b2 is the imaginary part, which was 0, 1. So this tells you that your x1 is going to be e to the 0t. x1 is going to be e to the 0t times b1 is going to be 1, 0. Cosine beta t is cosine t minus b2 is 0, 1. Sine beta t, beta is 1, so sine t. So this is going to be cosine t in negative sine t. Is that clear? Yes.
Can you explain how you got B1 and B2?
Say that again.
Can you explain how you got B1 and B2?
What about B1, B2?
Can you explain how you got B1 and B2?
B1 is the real part of the complex eigenvector. B2 is the imaginary part of the eigenvector. So that's where B1 is. I'm splitting it up into real part and imaginary part. B1 is the real part. B2 is the imaginary part. So that's how I'm getting it. Clear? Yes.
Can you explain again why you can just ignore the negative eigenvalue?
I did not because they're complex conjugates. They're going to differ by the sign, so it's the same thing with a different sign. However, I'm going to justify that at the back when I narrate the backstory to you. Okay, I'm not ignoring it really now. I'm going to justify it in the proof. Okay, let me not say don't need this. I'm going to say justify this in the proof. Okay, not the proof, but really somewhere some intuition, okay, some mathematical justification. I'm going to justify it at that time. Okay, clear? Okay, so now my x2 is going to be e to the 0 t times b1 is 1 0 sine t plus b2 is 0 1 cosine t. Then that gives me what? It gives me sine t and cosine t, right? So my general solution, x is going to be c1 cosine t negative sine t plus c2 sine t cosine t. That's my general solution. Right now I'm only saying what is the process, how am I evaluating. I'm not explaining you why. I will explain you why later. Are you okay with what am I doing, how am I doing? Okay, are we all together so far? So that is your general solution. Step 0 is to find the critical point, you did. Step 1 is to find eigenvalues, you did. Step 2 is to find the eigenvectors, you did. Step 3 is you memorize the formulas, you replicated the solution, you were able to find the solution, right? That's done. So what is left out? The next thing is you need to sketch the phase portrait. After that you need to get the direction of the motion or the arrows. After that you're going to classify the critical point. You are left with 3 more steps. Do you agree with me? Okay, let's begin that. So I did that, I didn't realize it. Okay, then that is what I have. Let's pick the next one. So I have x is gonna be c1 cosine t negative sine t. I think that's what I have. Bless you. Plus c2 sine t cosine t. This is what I have. Okay, so now I want to get the phase portrait. Okay, phase portrait. Okay, so when I get the how am I going to get the phase portrait? As she rightly pointed out with the with the circling of fingers. Yes, that's a phase portrait, but how do you get it? When t equals first I'm going to pick the value of c1 equals 1, c2 equals 0. So what does that give me? That gives you can do it for any c1 and c2, but I'm just picking easier case just to demonstrate it. Yes.
Why don't we make C1 and C2 just the same value?
You would get the same answer.
Is it easier, like, does the math work out better?
It just that the math will look easier and easy on ice and easier computations and easier sketch. That's all. Okay. So and we don't want to do the little rigorous computation. That's the only thing why we are picking it. So then my x is gonna be cosine t negative sine t, right? So when my t equals 0, my solution is really 1 and 0. When t equals pi over 2, my solution is 0 and negative 1. When t equals pi, my solution is negative 1 and a 0. When t is 3 pi over 2, if I make mistakes, let me know. 0 and positive 1. I'm repeating this again. If you think I made a mistake, don't hesitate. Just because I'm speaking louder doesn't mean I'm right. You can always contradict me. So when t equals 2 pi, I'm going to get x is going to be 1 and 0. So these are my solutions. So now if I'm sketching it, the rough sketch would look like at t equals 0, my vector is here. At t equals pi over 2, my vector is here. At t equals pi, my vector is here. At t equals 3 pi over 2, my vector is here. So my vector is really going in a closed loop around the critical point. It is not surprising because my solution has cosine and sine. Cosine and sine are periodic with period 2 pi. So that means the solution repeats itself after a certain amount of time. And it's not a surprise, my phase portrait is also repeating itself after a certain amount of time. Are you with me on that? This is when C1 equals 1 and C2 equals 0. So if I pick, let's say, C1 equals 2 and C2 equals 0, I would get a bigger circle, and so on, right? Do you see that now? If I make C1 as 3, I get even a bigger circle or a bigger loop, and so on. All good? Yes.
Does it matter how the direction of travel is?
I did not address the direction yet. I just gave you the phase portrait. Now I'm going to get to the orientation, okay?
Can you go to the back slide for just a second? Thomas, from the slide where you were rotating around. Oh. That was the chest where I thought you wrote something there, so I was like.
Okay? Then the next thing is I want to get the orientation right. So, or they refer to it as either the direction of the motion or the orientation, one of them. Or the orientation, right? So how am I going to pick? I'm going to write this as 0, 1, negative 1, 0. And I'm going to multiply it with, let's say, a vector on the x-axis. Then that gives me 1 and 0. Okay. Then this is negative 1, 0 and negative 1. Do you agree with me on that? So this means at this point, at that point, the screens go blank, and then when they come back, the direction vector will be pointing out in this direction. Is that right? Are you with me on that? Yes? So similarly, it's pretty much told you the story, but we want to repeat it just to make sure we are okay. Pick a point on the y-axis. I'm going to pick 0 and 1. So when I pick 0 and 1, and I multiply it with the matrix A, then what do I get? I get 1 and 0. So that means 1 unit is to the right, 0 unit is no vertical movement. So it is pointing out in this direction. So I multiply the matrix A, 0, 1, negative 1, 0 with the vector on the negative x-axis. So negative 1 and 0. So that gives me 0. Negative and 1, so that tells me that 0 units to the right side, 1 unit to the top, so I'm moving in that direction. So the last one is 0, 1, negative 1, 0 times 0, negative 1, so which gives me that negative 1 and a 0, that means I'm going in this direction. So you can see that I'm going in a clockwise direction, right? So that's why my arrows are indicated in the clockwise direction. So I'm going in the clockwise direction everywhere. Okay? Yes.
Oh, would there ever be a case where it goes counterclockwise? Sorry, if, well, like for this table, stable phase motion, will there ever be a case where it goes counterclockwise?
Yes, it depends on the matrix A.
Oh,
Yes, it is possible to have a stable center. Right, it is possible to have a stable center in the direction being counterclockwise, but that depends on the matrix A. So, for example, if I say, if I make this positive here, like if I make this positive, then that would make it counterclockwise. I don't know about eigenvalues and eigenvectors, but then just the direction would be clockwise, counterclockwise. Are you with me on that? Okay, so it is possible, but not in this problem. This problem is clockwise. Are you with me on that? Everybody good? So what did we do? So I'm going to classify 0, 0 is a stable center, a stable critical point, and 0, 0 is a center. So I found out what is my critical point. Do you agree with me on that? I found out what is my critical point. I found out what are my eigenvalues. I found out what are my eigenvectors. Then I told you that this is the formula. Go find the general solution. You found the general solution, right? After you get the general solution, I said, okay, how are we going to get? Just to simplify matters, I chose C1 as 1, C2 is 0. And I tried to get the phase portrait, right? And after that, I got the direction of the motion or the orientation. In this case, it was counterclockwise. Because the solutions are not going to zero, it is not asymptotically stable. Because the solutions are not going away from the zero, they are not unstable. Because they are going in a circle, in a closed loop at a certain distance, the solution is stable. Is that clear? We are done with the problem. Do you agree with me on that? Yes? Now the only thing is, like, is there any other way that, now the backstory, okay? It's always good to have a backstory so that you appreciate the math better. I mean, otherwise why differential equations? This you could have done even in the last semester, right? You see what I mean? You could have done this in the last semester. So what is the backstory? The backstory is this. Let's go with that. That's what is interesting, right? X prime is 0, 1, negative 1, 0 times x. Correct? Do you agree? Did I get it right? Okay. So I can write this as x1 prime, x2 prime is going to be, okay. This is not for the test, just for fun. Okay. You know what I mean with that. Okay. 0, 1, negative 1, 0 times x1, x2. If I'm teaching you just for the test, like I will be done in half an hour, so 7.5 hours, we are done with the semester, okay? You get nothing out of that. So you get x1 prime is going to be, did I get this problem right? Yeah, x2, then I get x2 prime is going to be negative x1. Do you agree with me on that? I cannot use first order differential equation. I cannot use variable separable. Allow me to rewrite this as dx1 dt is going to be x2, dx2 dt is going to be negative x1. Right? Do you agree with me on that? Now, somewhere in calculus, you must have studied the calculus of polar coordinates or introducing the parameter, eliminating the parameter. You must have studied all that in calculus, right? If I'm right, you must have studied it in 1552, where you found out the surface area when you're revolving a curve about a certain axis and all that kind of stuff. So this will lead you to, dx, if I'm eliminating the parameter, this would give me negative x1 over x2. Do you agree? Like it's like the bottom equation divided by the top equation, and you should never say it, the dt gets cancelled out and this is what you get, but you should not say that. Are you with me? Yes? Yeah. Now the wonderful things happen. What is that? This is variable separable. Do you agree? Yes or no? See, x2 dx2 is negative x1 dx1. You want to integrate both sides. When you integrate both sides, you get x2 squared divided by 2 is negative x1 squared divided by 2 plus c1. So you get, multiplied with 2. So you get x2 squared equals negative x1 squared plus c, where my c is 2c1. Then you get x1 squared plus x2 squared equals c. Then this tells you that this is a circle with center 0, 0 and radius square root of c. Do you agree with me on that? So you see, you can look at it this way. So you can justify it using variable separable, that your trajectories or solution trajectories are always circles with centered at 0, 0. You see that? It can be done. Okay? So don't think like just, now you can see the connection between the first order scalar differential equations and systems. It's like, they are very closely related still. Okay? Is that clear? This is again just for fun. All good?
Does it say anything below square root of c?
Nothing. Okay? Okay, one other question you should have asked me and you did not. I'm gonna pause. Do you want to ask me any question from this slide to, he already asked me. Are you ignoring this? Why are you ignoring this? Who asked me? You asked me. Good question. I don't know your name, but good question. No bonus points though. Okay, very good question. So I'm gonna answer his question, and it's all his fault now. Okay, so let's go with this one. So I got my system with x prime equals ax, right? Agreed? And I got my eigenvalues to be alpha plus minus I beta. Okay? My eigenvectors were beta b1 plus minus ib2. Agreed? When my eigenvalue has a plus sign, my eigenvector has a plus sign. When my eigenvector has a negative sign, when my eigenvalue has a negative sign, I get a conjugate eigenvector as well. Do you agree with me on that? And my solution is like, let's say I am so naive, and then I would say, okay, my solution would be just like I want to imitate what happened in the real and different case. So I want to write, okay, C1 e to the alpha plus I beta t times, what do I write? I write B1 plus IB2 plus, C2 e to the alpha minus I beta t times beta B1 minus IB2. Do you agree with me on that? I would write that, right? Yes or no? Again, this is not for the test. Not for the test and just for fun. I mean, I'm just doing it so that you justify, why sign, where are sines and cosines coming from? Why am I ignoring the other eigenvector? I'm tying up that loose end. Just for fun. You can just sit and watch this one. I mean, no need to write this. So then this one would be, the natural thing would be, I would say, okay, e to the alpha t is the greatest common factor. So I want to really factor it out. Then I get B1 plus IB2 plus C2 times e to the negative I beta t times B1 negative I beta IB2. Agreed? Yes? And thanks to Euler, we know that e to the alpha t is going to be C1 cosine beta t plus I sine beta t times B1 plus IB2 plus C2 times, cosine beta t minus I sine beta t times B1 minus IB2, right? You know the Euler's formula, e to the I theta is cosine theta plus I sine theta. When you studied complex numbers, you must have studied that as well. Are you with me on that? Are we all together so far? Say yes or no. This is not going to be on the test, so you can be like fearless and say, are you understanding it or not? That's all. This is just for fun, Are you with me? Good. So then what is the next thing we would do? I mean, the natural thing we would do is, because I see two terms and two terms, I want to multiply it out, distribute the terms and see what happens. Does anything fantastic come out of it? Luckily for us, something fantastic really happens. What is that? It is B1 cosine beta t, then plus IB2 cosine beta t, plus IB1 sine beta t. I times I is I squared is negative 1. So minus B2 sine beta t. Okay. Now plus C2 times, cosine beta t times B1 is B1 cosine beta t. Oh, I should have not used C1 and C2, but it's okay. I don't want to erase it now. Cosine beta t times negative IB2 is negative IB2 cosine beta t. Then negative I sine, this will give me negative IB1 sine beta t. Right? Are you with me? Negative times negative is positive. I times I is I squared. I squared is -1. Negative b2 sine beta t. How nice. Right? So then, okay, now that I distributed the terms, what am I gaining out of it? Am I really gaining anything out of it? First thing is I got cosine and sine, right? Cosine and sine are periodic with period 2 pi. So that explains why my solutions are going in a circle in this problem. So there is a periodicity of the solution is attributed to the presence of sine and cosine. And sine, you will only see sine and cosine when you expand I beta in using Euler's formula. So the next thing you can see that is that these are the, e to the alpha t, b1 cosine beta t is the greatest common factor here. So I can write this as b1 cosine beta t times c1 plus c2. Do you agree? Please stay with me. Make all your effort to stay with me. Don't leave me. Okay? Don't isolate me there. Now, the next thing is you are going to real part. You're running after real parts. b2 sine beta t, negative b2 sine beta t. Again, if you factor out negative b2 sine beta t, that gives you c1 plus c2. How fantastic. You see c1 plus c2, c1 plus c2. It's as if the symmetry exists in the universe for real. Then the next thing is, these terms are greatest common factors. So factor that out. You are factoring out b2 cosine beta t. So what is that? What remains is c1i minus c2i. Okay. So now we are hoping and praying secretly, at least me, that these two will also give me that. So I'm going to factor out b1 sine beta t. That gives me what? c1i minus c2i. Fantastic, right? Amazing. Right? So now I want to rename this. What do I want to rename? How do I want to rename this? I want to rename c1 plus c2 as k1. And c1i minus c2i as k2. So this gives me, okay, now I'm going to go back and forth, forgive me for that. My solution x is going to be e to the alpha t, is going to be is going to be k1, k1 b1 cosine beta t. K1 minus k1 b2 sine beta t. Okay, then from here it's going to be k2. So it's going to be k2 b1 b1 sine beta t plus k2 b2 cosine beta t. This is what I get. Remember, my solution is a vector. b1 is a vector, b2 is a vector, b1 is a vector, b2 is a vector. So my left side is a vector, my right side is a vector. So now I can see that you can write that x equals what is that? K1 times e to the alpha t times b1 cosine beta t minus b2 sine beta t. Plus k2 times e to the alpha t times b1 sine beta t plus b2 cosine beta t. So this is same thing as k1 x1 plus k2 x2. So nothing is lost. It's still in the same thing, right? So when you get bored on a Friday evening, just sit at it and stare at it. You will see the beauty in it. So now going back to your question, did we ignore the other eigenvector? We did not, because the other eigenvector was right there. And that really, when we use the Euler's formula, got embedded into the solution. Is that clear? Are you all with me on that? The other great thing that happened was, when here my eigenvectors were complex, but here what I did was I transferred the complexity from the eigenvector onto the arbitrary constant. Now my eigenvectors are real. When I got to x1 and x2, my eigenvectors are real valued functions, but my constants are complex valued constants. Do you see that? That's another big thing that I did, because sketching the complex valued solutions is really a tough deal. So what we did was we transformed the complex valued eigenvectors into a real valued functions, and we transformed the real constants into the complex constants. Is that clear? That's another great thing that we have done in the process. Clear? Any questions? I in my head, I tied up all the loose ends as well. Yes.
So in the general solution formula that you gave us before, you didn't have like the K1 on the outside.
But I have C1, C2. So C1, C2 are complex constants at that time.
Okay, so do C1 and C2 always equal 1? Because like the coefficient is 1 in the formula that you gave us before. It was on 52, I think.
This one?
Yeah.
So what is your question now?
Well, like there's no K1, K2.
Yeah, this is like in place of C1 and C2, use K1, K2.
Oh, okay.
You see what I mean?
I see what you mean.
I mean, you know, I can write C1 is gonna be, what is that? K1 plus K2 here, like in, mean, you know, I should not have, I made a mistake, like, you know, because, not a mistake, that's a confusion because I made C1, C2, I should have made K1 and K2. All that I care is there is an arbitrary constant which are complex value,
Yeah.
that's all.
Okay, I see what you mean.
Clear? Okay, everyone on board? Yes.
Okay, the complex number.
My arbitrary constants are complex because my K2 here is a C1i minus C2i. They're complex. That's why my K2 is a complex constant. That's not a real constant. But my eigenvector is a real valued function. My eigenvector is not complex values. So that's a great thing. Big thing. Yeah.
So instead of lambda 1, if we use lambda 2 in the previous problem,
You would exactly get
get
the same.
So
Right. Yeah. I tried it out. I did not demonstrate it here.
Yeah, no, but if you just
But,
look
yeah.
at the sign.
Yes. See, the reason is, but I can tell you, I can intuitively justify it. The reason being, you see, in this mathematical justification, I started out with C1, first eigenvalue and eigenvector, second eigenvalue and second eigenvector. Both of them in combination will give me this. So I'm not really ignoring the other one as such. You see that? Clear? All good? I don't know the names, so I can't ask. Okay. No, I know few names. I don't want to just. Okay, now let's go with the next problem. Okay, the next problem is it okay? Let's see how comfortable we are, and then we will assess the situation. This next matrix is this, right? System of equations is this. So is it okay? Are you comfortable if I say but after carrying out the computation, my eigenvalues would be plus minus 2i? Are you comfortable with that?
Yeah.
Can I skip the computation and just say that? Okay, then let's say if I'm going with lambda equals 2i, then my eigenvector would turn out to be 1 and 2i. Are you comfortable with that?
Yeah.
Okay, then I mean, you know, let me write out in here, I can write alpha is 0, beta is 2 because the real part is, I'm getting a purely imaginary complex eigenvalue. So my real part is 0, my complex value is 2. In this one, I can split it out as 1 and 0 plus I times 0 and 2. So this is my B1 is 1, 0, my B2 is 0, 2. Do you agree with me on that? Okay.
Just a question, is there any reason for assigning this B, is this related to the value of beta or not at all?
B1 and beta are not connected. I ran out of alphabets, so I chose B1 and B2. They are not connected. Eigenvalues are numbers, eigenvectors are vectors, so they are not connected. Except that for when my eigenvalue is 2i, my eigenvector is 1 and 2i. Except for that, there is nothing. Okay, are you with me? Now let me draw your attention to, I hope you find it cool, but let me draw your attention to this one. So in this one, you see when I did that, when I was doing this 1001, right? This told me that it is a circle, unit circle, right? Are you with me on that? But when you see this here for this problem, it is 10 and 02. So what do you think it is going to be? It's going to be ellipse. So ellipse means, don't leave me with ellipse means is the transverse axis vertical or horizontal? What do you think is going to be? Vertical. Why is it vertical? Because the 2 is at the 2 is because the 2 is with the y component. Your intuition says that the ellipse is going to be vertical. Do you agree with me on that? Okay, then I sketched it and it turns out to be that way, but I'm not, we are going to get to the justification very soon. And is it okay, the real part is 10, the imaginary part is 02, then you're going to use the formula and get the general solution to be this way. Is that okay with you all? Clear? And then the next thing that I want to tell you is that is it okay to say it is going to be elliptic and orientation? Can I leave it as an exercise for you? Direction of orientation, you would be able to figure it out. And it's going in the counterclockwise direction as well. Are you okay with that? There is a reason why I'm skipping. Meaning I'm not tricking you on this one. More the trick problem follows. So I want to go there and explain in detail. This is an easier problem just like the previous one. So, I mean, why do the same thing, right? So that's what I'm thinking. So then it's going to be a stable center. It's not going to the origin. So it's not asymptotically stable. It's not going away from the origin. So it's not unstable. It is going at a certain distance around the origin. So it is stable center. Are you okay with that? The critical point 0, 0 is the center. Is a center. You with me on that? Clear? All good? Yeah. Clear? Is the process and the computation clear in your head? Good. Now, let me ask you. So, I don't know the answer to this. I'm just posing, I'm thinking it loud with you. So, if I'm working in SpaceX and let's say I want to launch a satellite that goes around the Earth in a circular fashion. So, do I launch my satellite that follows this differential equation? I don't know. That could be a good question, right? No, you see, if the differential equation is like this, my solution is like that, and my solution, the trajectory is circular, right? It's a stable center. Mathematically, it's proven that it keeps going around in the center, right? As long as there is no external factors. So, if now I'm thinking it loud. So, if I want to launch satellite that goes around the Earth in a counterclockwise direction at a certain distance forever. So, do I launch a satellite in such a way that my differential equation follows this? With this differential equation in mind. I don't know, but that could be a good starting point to think. Okay. Now, the next problem is, okay, now I'm picking a different problem. This is again an easier problem, nothing complex. 0, 0 is the critical point. These are my eigenvalues. So my alpha is 0. My beta is 1/2. So this is my eigenvector. So I'm going to break this into 2, 0 plus I times 0, 1. So this is my B1. That is my B2. Right? So now, do you think is it going to be, what is the trajectory is going to be? Is it circular or ellipse? What do you think? Ellipse, right? So now, is the transverse axis vertical or horizontal? Why? Because of the presence of the 2 here, right? Are you with me on that? So I just use a simulation and it is, that's not surprising. So if I want a vertical ellipse, then I wanted a different differential equation. I wanted like a horizontal ellipse. I want a different differential equation. So now by just replicating the formula, you will get the solution. Are you comfortable with the solution? Okay, then we would say the critical point is stable and the critical point is a center. No discussion, nothing complex in this. It just follows a normal computations, straightforward computations, nothing complex in this. Clear? You all okay with that? All good? I promise you, there are no. Yes? Do you have questions? No. Okay, the next problem is that. So this is what I wanted to talk about. I mean, this is. Let's go back to our slides a little more, a little bit here. I have 3 cases when my eigenvalues are complex. My real part is positive, real part is negative, real part is 0, right? When the real part is positive, they are spiraling away from the origin. When the real part is negative, they are spiraling towards the origin. When the real part is 0, it's a stable center. It's going in a circular loop. And for till now, I'm just concentrating on the third case, right? Do you see? I'm spending all my energies only in the third case. I'm like, I'm saying, how do you know it is a circle or an ellipse? Transfer whether the ellipse is horizontal or vertical, different ways to look at the problem and analyze it. So that's what I'm working on. So the next one is going to be a problem, this one. Let's see. This one is going to be, is it okay to say that 0, step 0 is like, I want to get into a little bit of detail on this problem, but a lot of it will remain the same or just tiny bit will change. So my determinant of A is going to be, in this case, negative 16 plus 25. So that's going to be 9. So A is non-singular. So A inverse exists. So this tells me that 0, 0 is the critical point. This is not a surprise. We are good with it, right? This is what it is. Are you okay? The next thing is I want to find step 1 is to find eigenvalues, and my eigenvalues are plus minus 3i. So that tells me my alpha is 0, my beta is 3. Okay? Alpha is 0, beta is 3. Nothing complex, no tricks, I promise you on that. Then the next thing is, okay, I want to find eigenvector corresponding to 3i. Then I got my eigenvector to be 5 and 4 minus 3i. So I get 5, 4 plus I times 0, negative 3. Do you agree with me on that? So this is where, see, in the previous eigenvectors, I got the real part or the imaginary part, this component was 0, then I would get an ellipse with whose transverse axis is horizontal. Are you with me on that? Because the bigger component is 5, it's along the x-axis, so that's how I would go after that. Do you agree with me on that? But this one says 4, so that's where the issue comes in. So now what do you think is going to be the trajectories? Okay, let's see. So this is my solution. Is that clear? So now I'm going to say, okay, my alpha is 0, my beta is 3, my B1 is 5, 4, my B1 is 5, 4, my B2 is 0, negative 3. So I'm going to use my formulas e to the alpha t. Nothing tricky here. Cosine bt minus b2 sine bt beta t, and x2 is e to the alpha t b1 sine beta t plus b2 cosine beta t. So my x is going to be c1 x1 plus c2 x2. So if I run through the process, this is my solution. Agree? Are you all okay with that? Are you all okay with that? Yes? Okay, so now I want to get the face portrait. Okay, I want to get the face portrait. So how am I going to get face portrait? My solution here is C1 5 cosine 3t 4 cosine 3t plus 3 sine 3t plus C2 times 5 sine 3t. Then it is 4 sine 3t minus 3 cosine 3t. Okay, this is my solution. So I'm going to put in again C1 is 1 because I want to get the rough, I want to get the face portrait. I want to approximate it with easier computations. So C1 is 1, C2 is 0. This tells me that my x is going to be 5 cosine 3t 4 cosine 3t plus 3 sine 3t. Do you agree? Okay. Yes? Then obviously, as you know now, I'm going to put t equals 0. So my solution vector is going to be 5, 4. So that's somewhere 5 and 4 is somewhere there. The vector is right there, right? The terminal point of the vector is right there. And when t equals pi over 2, my solution vector is 5 cosine 3 pi over 2. That's a 0 there. Then cosine 3 pi over 2 would be 0 again. Sine 3 pi over 2 would be -1. So 0 and -3. So my solution, my vector would be here. The terminal point of the vector would be somewhere there. Do you agree with me on that? Yes? Right? It's really amazing, right? You see, t equals pi. My solution is going to be, when t is pi, I'm going to get -5, -4. So -5, -4 is somewhere there. Right? Okay. The other one is t equals 3 pi over 2 would be what? My solution vector is going to be t equals 3 pi over 2. Then it's going to be 5 and 4, because 9 pi over 2 is same as pi over 2. So this is 5 and 4. So this is going to be, is it 5 and 4? What did I miss? Three pi over 2, that's going to give me something else. I missed something. 3 pi over 2, 9 pi over 2, cosine 9 pi over 2 is 0. Cosine pi over 2 is 0, but that gives me positive 3. So that gives me 0 and 3. So somewhere there. And when t is 2 pi, I'm getting really, again, my solution vector is going to be same thing as when t is 0, 5 and 4. So this is not going to be, I have sine and cosine in my solution. So they are not lines, they are not curves, they are periodic with certain period. So they are really, this is an ellipse. This is rotated by a certain angle. My ellipse is really bad, but my sketch is bad, but that is an ellipse. Are you okay with that? So it depends on how I want to launch my satellite, right? If it is circular, then I want the differential equation of first kind. If it's elliptic, then certain thing. If it's at a certain angle. So what is left? Really, what is left is the orientation or the direction of the motion, or the orientation. That's the only thing that is left in the classification. So remember, how do I determine that? I'm going to go with this 4, -5, 5, -4. Pick a vector at 1, 0. And then multiply it, then you get 4 and 5. So this tells you that if I'm standing it at 1, 0, I'm being pulled 4 units to my right, 5 units to the top. So I'm moving in this direction. So this is what is my direction. So this is counterclockwise. That answers your question. The critical point can be stable but still go in a counterclockwise direction. This is when C1 C1 is 1 and C2 is 0. So this is when C1 is 1 and C2 is 0. Do you agree with me on that? Yes.
Well, why would, I guess, why would it be clockwise? Or I guess, why would it be clockwise? Because like, when she's like, because like, when she's increasing, it's going in this direction.
Why would be counterclockwise? That's what is your question, right?
Yeah.
Because when it is like that matrix when acts upon 1, 0, I'm getting 4 and 5, right? Do you agree with me on that? So that means if I'm standing here, I'm being pulled 4 units to my right, 5 units to the top, right? Yes or no? So that means my direction is this. So this tells you that I'm going to the top right corner. So that means that tells you that it is counterclockwise. Then once I go here, I need to turn because that's my trajectory. Are you with me? Is everyone on board with this idea? So,
Sorry, can you go to that side and click on to see which point you were looking at?
say that again.
What was the point you were like looking at, like for this? Why did you choose 1, 0? Like, was it just random?
Why did I choose this one, right? Because I'm seeing, like, if when I multiply ax equals b, I'm thinking this is the transformation of x that is giving b, or like the displacement is the x and the velocity is b. So I'm saying when the force is acting on me, when I'm standing at 1, 0, I'm experiencing my velocity is in the direction of 4, 5. No, you didn't get it. Okay, I'll repeat myself again. Why am I picking 1, 0? I just want to see the direction. So I could have picked anything inside, how is it being pulled? That's all. So I can pick 1, 0, or I can pick 2, 0, I can pick 3, 0. How is the force being experienced? In what direction is the force being experienced? That's all. Okay? Are you okay with that? So now, if for a different value of C1 and C2, I'm going to get a bigger ellipse like this. I can pick a different ellipse again. So then for a different value of C1 and C2, I get a bigger ellipse like that, and so on and so forth. Those are my trajectories. Does that make sense? Is that clear? Are you with me? So I have just 5 minutes, so the fun part begins. This is for the test, right? And the critical point is stable but not asymptotically stable, so that's not a surprise, so you are okay with it. Correct? So now if you look at it, that's a computer simulation now. Now if you look at it, I mean, I have dx1 dt is going to be from here, 4x1 minus 5x2. And dx2 dt is going to be 5x1 minus 4x2. Then from here I can write dx2 dx1 is going to be 5x1 minus 4x2 divided by 4x1 5x2. Okay. And then I use a method called method of substitution. Now I'm hand waving a lot of detail just for fun. This is again not for the test, just for fun, so that you don't get worried about it. I use method of substitution. I get my solution like this. This is my implicit solution. Is that clear? Are you with me on that? Okay, now if I get that as an implicit solution, you see this is my quadratic form. Do you agree with me? Why is it quadratic? Because exponent of x is 2, y is 2. Now you learned in 15 linear algebra or 1554, 1553 or 1564, I don't know what it is, but you can write that quadratic form in a matrix notation using matrix notation like that. Are you comfortable with that? Now I'm just hand waving a lot of details, okay? I'm just like, I have 5 minutes. This is not for the test. This is just to make ourselves feel good. So that's what it is. So, but then if I have the matrix 5, -4, -4, 5, it is diagonalizable. The eigenvalues are 9 and 1, and the corresponding eigenvectors are these. So this quadratic form, this solution, implicit solution, can be written in the quadratic form, can be written in a diagonalizable form like this using similarity of transformation, and that when you multiply it will reduce to this. And if you apply the transformation of rotation and all that, you get 9u squared plus v squared, which is nothing but an ellipse rotated by a certain angle. Do you see that? So I just wanted, I mean, you know, previously I showed you how you using variable separable. It was a circle with center 0, 0 and radius square root c. Now I knew I would, by the time, because of my experience, by the time I finish this explanation, I'll have just 2 minutes. So I want to hand wave a lot of details and explain that you will really end up with an ellipse rotated about a certain angle because of a certain transformation. Are you with me on that? Using your knowledge of quadratic forms and diagonalizability from your linear algebra. So now you can see how they are inseparable, meaning linear algebra and differential equation. One cannot go without the other. It's just like, you know, you teach in different semesters, but they are one and the same. So is that clear? So this is just for fun. I mean, you know, try it out. I mean, this is really interesting. But now the summary of this class is this. I have a system of first order differential equations. My eigenvalues are complex. In this class, we only spoke about eigenvalues are purely imaginary. The real parts are 0. Critical point was stable. Critical point was a center. You found eigenvalues, you found eigenvectors, you were able to get the general solution, determine the direction, and classify the critical point. And we also went little bit in detail to see how we got it into the form of, in the terms of sine and cosine, and how we transformed the complex solutions into the real valued function. That's all we did. So when we come back on Thursday, we're going to see what happens if your real part is not 0. In this entire discussion, real part was 0. What will happen if your real part is not 0? That we will see in the next lecture. Okay? That's all I have for today.